So I'm here from the National Museum of Mathematics. My colleague Cindy Lawrence, you heard from earlier. It's a view of the front of the museum. And it's a museum, we've tried to fill it as chock full of interesting things as we can, so there's lots to talk about, but with only 6 minutes, I'm going to talk about just one exhibit at the Museum of Mathematics. It's called the Mathenaeum. And it's a sculpture studio of sorts. It's a polyhedral sculpture studio. You use this device here to construct various polyhedra. And the giant clear trackball in the center is sort of your avatar for the polyhedron you're constructing. It's a three-axis trackball. Anything you do to that trackball, the image that you're creating will rotate. And then there are various bars and throttle to select various operations. You start by picking a base polyhedron. You can see here somebody's about to pick an antiprism, a square antiprism to start with. And once you've picked your starting thing, you can do various operations and create stuff like this. And there's a gallery, and you can show off your creations in the museum, and so on. So what are these operations that you can do on the polyhedra? Well, they're sort of been called kind of the Conway operations, a number of basic operations that you can do on polyhedra to make new polyhedra. And also, I thought I'd throw them just to see how high a percentage of talks here today could mention John Conway's name. I think we're doing pretty well so far. So anyhow, what are they? Well, you can take the dual of any polyhedron that you've created so far. So replace, swap faces and vertices. You can truncate any polyhedron that you've created so far. Here you can see various stages of truncation of a cube, and so you can truncate sort of all the way down to a cube octahedron, but with that throttle, the Mathenaeum lets you truncate any amount you like. You're also not required to truncate every single vertex. You can pick some subset of vertices to truncate if you like. You can elevate. Here you can see an elevation of a cube. All that means is that we've added a vertex at the center of every face and pulled it out, creating a pyramid on top of every face. You can expand, or here it's called cantillation, but we call it expansion, which is to just take all of the faces here. We're doing it to a cube. Take all of the faces of the polyhedron. You move them out from the center of the polyhedron, keeping their orientations and spaces, moving apart from each other, and you fill in the gaps with new faces. So that's the expansion of a polyhedron. You can snub a polyhedron. Here's a snub dodecahedron and a snub cube. At the Mathenaeum, you can snub any polyhedron that you make, which is just like expansion, except as the faces move out from the center, they also rotate in their own planes, and then you have to fill in the spaces with slightly differently than you do in the case of expansion. You can see what's going on there. You can extrude. Sorry, I used a stock photo without paying, so mea culpa. You can extrude from the faces of the polyhedron, which just means raise a prism on the faces of the polyhedron. And you can stellate, or when John visited the museum, what he called gratify, which is to say extend the planes of all the faces until they meet again at new edges. So you can see this is the stellation of a dodecahedron. Every one of those 5-pointed stars is in the plane of an original face of the dodecahedron. So those are the operations you can do. And with them, and you can also sort of decorate things. You can put spheres at the vertices. You can thicken the edges. You can color the faces. And now with those basic operations, you can create quite an amazing array of different polyhedra. And visitors will spend quite a bit of time with this. These are all visitor-created objects. Just a little gallery of some of the possibilities that people have created. And then, as I mentioned, you can show these off in the museum, and we actually 3D print a lot of these and put them on display in the museum so that visitors can see what other visitors have created and be inspired to try new ideas of their own. And I would have loved to give everybody a 3D printed copy of one of these models, but 350 different 3D printed models was a lot. So instead, you're going to have to satisfy yourself with a beautiful two-dimensional print of a three-dimensional object. And don't miss the back because there's don't miss the back because there's an important announcement on the back. We hope that some of you will be interested in our own recreational mathematics conference, which will be next summer. But now, if you read the description of the giveaway, it has a lie in it. It claimed that there were going to be 350 different polyhedra, because we have thousands of these polyhedra that people have created. But creating each one of these snapshots took a little bit of work to find a nice camera angle to get a good shot. So I got tired. There are 175 different ones. So there's 2 of each, which means there's also a little bit of a game here, which is that if you can find your matching polyhedron, right? So the first pair if we go back to the computer here, the first pair that emails a photo of the 2 of you with matching polyhedra to Whitney@momath.org with subject line G4G11 matching game, I will send you, and this is also to create a tenuous link with my colleague's talk, I will send you a Pythagoras the Flatiron t-shirt as a prize for being the first one to find matching polyhedra. So, okay, but I did promise a math problem of some substance, which finding matching is fun, but it's not exactly a math problem of substance. So here's the math problem of substance, and it goes back to that first operation that I barely even mentioned, the dual operation, which has been the thorn in our computational geometry side in implementing the Mathenaeum. If you look at this polyhedron, you will notice a subtle crease in those top faces. That's because they didn't come out planar, and so we add an extra edge, which we didn't highlight to try to kind of sweep this under the rug, but the face of that polyhedron is not planar. So it's easy for us to make a sort of geometric dual of the polyhedra that we're working with. We put a vertex at the center of every face, and then we sort of triangulate that set of vertices, and that's what we're doing right now. Or it's easy to do the combinatorial dual and make the graph, which is the dual of the graph of the polyhedron. But what we would, of course, like is to do something that's both. Create a polyhedron, which is the dual of the polyhedron that the person, both the sort of the vertices obviously can't be at the centers of the faces, but it should be, graph theoretically be the dual of the original polyhedron, and it should be a polyhedron. All the faces should be planar. So I gave a similar talk at MIT, and somebody said, oh, that's easy. All you need to know about is Steinnitz's theorem. Steinnitz's theorem says that any graph, which is the graph of the vertices of a polyhedron, it can be embedded to form a polyhedron. In fact, it can be done in such a way so that all of the faces are tangent to a given sphere, and there are algorithms in these papers. Just implement it. So we had somebody try to implement a couple of the different algorithms that are published, and they work fine for polyhedra with 8 faces, 10 faces. But we have people making stuff like this, and the algorithms are completely hopeless, completely intractable over maybe 15 or 20 faces. So if you know a computationally tractable way to make the dual of a polyhedron, which is its graph theoretical dual, and which is also a polyhedron with planar faces, please let us know. Thanks so much.